When the James Webb Space Telescope opened its eyes, it didn't just sharpen our view of the universe, it shattered some of our most basic assumptions about what a planet can be. Instead of familiar worlds neatly fitting our models, Webb revealed objects that seem almost impossible. Planets stretched into strange shapes by gravity, worlds so light they're closer to cotton candy than rock, and bodies that blur the line between planets and stars themselves. These discoveries aren't just unusual, they directly challenge how planets are supposed to form, survive, and evolve. From pulsar-orbiting worlds forged under extreme physics to rogue planetary pairs drifting through stellar nurseries, Webb has uncovered a cosmic zoo that refuses to play by the rules. Do not forget to leave a like and subscribe to the channel because tonight we're exploring the strangest planets ever found by the James Webb Space Telescope and why their existence is forcing scientists to rethink the very definition of a planet. Get ready, we begin. There is a planet shaped like a lemon, not metaphorically, not approximately, a lemon. It orbits something that shouldn't allow planets to exist at all. Something that should have destroyed it billions of years ago. Something that tears apart everything that comes near it. And yet this planet remains, stretched, distorted, defying every model we have about how planets form, how they survive, and what they're made of. The discovery was announced quietly in 2023. Most news outlets ignored it. But the scientists who found it couldn't sleep for weeks. Because if this planet exists, then our understanding of planetary formation isn't just incomplete. It might be fundamentally wrong. But that's only the beginning. There is another world out there, less dense than cotton candy. An entire planet, larger than Jupiter, that you could theoretically walk through. Its atmosphere extends so far into space that it shouldn't exist at all. The laws of physics suggest it should have evaporated billions of years ago, stripped away by its star's radiation. Yet there it floats, impossibly puffy, impossibly stable, impossibly real. When astronomers first calculated its density, they thought their instruments had malfunctioned. They recalculated, then recalculated again. The numbers didn't change. The planet remained impossible. And then there's the diamond world, a planet where the surface temperature reaches 5,000 degrees, where oceans of lava lap against shores of graphite, where the pressure deep inside is so intense that carbon crystallizes into structures we can barely imagine. A world where it might literally rain diamonds, where the core could contain more compressed carbon than exists in Earth's entire crust, where geology becomes something else entirely, something we don't have words for yet. The planet orbits so close to its star that a year there lasts just 18 hours. 18 hours of unimaginable heat, unimaginable pressure, unimaginable strangeness. But perhaps the most unsettling discovery isn't a single planet at all. It's a population, dozens of them, maybe hundreds, worlds the size of Jupiter, floating free in space, untethered to any star. Some of them orbiting each other in pairs, locked in gravitational dances that shouldn't be possible. They formed like stars but never quite became stars. They exist in a category we didn't know existed until we found them. Orphan worlds, rogue planets, binary systems with no sun. They're out there right now, drifting through the dark spaces between stars, and we have no idea how many there might be. The discovery came from images of a stellar nursery, a place where stars are born. Except these things aren't quite stars, and they might not be quite planets either. Then there are the superpuffs, worlds so inflated, so impossibly low in density, that they challenge our understanding of what matter can do. Entire planetary systems of them, all orbiting the same star, all displaying the same impossible properties. Their atmospheres extend for hundreds of thousands of kilometers. Their gravity is so weak that standing on their surfaces, if they have surfaces, you would weigh almost nothing. They should collapse under their own gravity. They should be ripped apart by tidal forces. They should have lost their atmospheres billions of years ago. They should not exist, but they do exist. 3 of them, maybe more. All in one system, all defying explanation. Something is wrong with our models, or something is right in ways we never imagined. These planets exist in our universe, orbiting real stars, subject to the same physical laws as Earth. Yet they behave as if those laws have exceptions we never wrote down, as if reality has loopholes we never considered, as if the universe is stranger than we dreamed, and we're only now beginning to see just how strange it really is. The observations are clear. The data is solid. These worlds are real. But the explanations are where everything falls apart. What follows is not just a catalogue of weird planets. It's a journey into the places where our understanding breaks down, where the models fail, where the universe reveals itself to be more creative, more bizarre, and more unsettling than any science fiction writer ever imagined. These discoveries were made by real telescopes, analysed by real scientists, published in real peer-reviewed journals. They are not speculation. They are not theory. They are observation. They are what's actually out there, and they're waiting for us to figure out what they mean. The pulsar was discovered first. Pulsars are what remain after massive stars explode in supernovae. The star's core collapses into an object so dense that a teaspoon of its material would weigh 1 billion tons. It spins hundreds of times per second, firing beams of radiation from its magnetic poles like a cosmic lighthouse. These beams sweep across space with such precision that pulsars can be used as clocks, keeping time more accurately than any device humans have ever built. They are incredibly hostile environments. The radiation is lethal. The magnetic fields are the strongest in the universe. The gravity is so intense that it warps space-time itself. Nothing should survive near a pulsar, certainly not a planet. PSR J232, 2650, is located about 5,000 light-years from Earth in the constellation Aquarius. It's a millisecond pulsar, spinning 368 times per second. When astronomers study pulsars, they look for regularities in the pulses. Variations in timing can reveal unseen companions, planets, or other objects orbiting the pulsar and causing tiny gravitational perturbations. In 2023, a team analysing data from multiple radio telescopes noticed something strange in PSR J232222650's timing pattern. The variation suggested a massive companion, something with the mass of Jupiter, something that shouldn't exist. Because pulsars are born in supernovae, and supernovae destroy everything nearby. Any planets that existed before the star exploded should have been vaporized, obliterated, reduced to their component atoms and scattered across interstellar space. But the data was undeniable. There was something there, something big, something orbiting the pulsar every 190 days. The team published their findings. Other teams confirmed the observations. The planet was real, but how it got there, how it formed, how it survived, none of that made sense. Pulsars can have planets, but they're rare, and they're usually small, formed from the debris of the supernova itself. This was different. This was a gas giant. This was something that looked like it had formed the normal way through the slow accumulation of gas and dust around a young star. Except there was no young star. There was only the corpse of an old one. Then came the modelling. Researchers began to calculate what the environment near the pulsar would do to a planet. The radiation pressure, the magnetic fields, the tidal forces. What they found was even stranger than the planet's existence. The tidal forces from the pulsar's intense gravity would be so strong that they would physically distort the planet, stretch it, elongate it, pull it into a shape that resembled not a sphere but an ellipsoid, a lemon. The team ran simulations. They calculated how much the planet would be stretched. They estimated its shape based on its mass and orbital distance. The results were clear. If a Jupiter-mass planet orbited PSR J2322-2650 at the observed distance, it wouldn't be round. It would be stretched along the axis pointing toward the pulsar, compressed along the perpendicular axis. It would be quite literally lemon-shaped. But the strangeness didn't end with the shape. The planet's composition became the next mystery. Gas giants in normal solar systems are made mostly of hydrogen and helium, with traces of heavier elements. But this planet formed in an environment rich in heavier elements, in the debris cloud of a supernova. Carbon, oxygen, silicon, elements forged in the dying star's core and blasted into space during the explosion. The planet would have accreted these heavier elements in unusual proportions. Its atmosphere might be carbon-rich. Its interior might contain layers of exotic ices and compressed materials. And deep inside, under pressures millions of times greater than Earth's atmospheric pressure, carbon might crystallize, might form structures we associate with diamonds. The planet might have a diamond core, not a small one, not a symbolic one. A core of crystallized carbon hundreds or thousands of kilometers across. This is where the language starts to fail. We use the word planet, but PSR J2322-2650 isn't like any planet in our solar system. It exists in an environment so extreme that matter behaves differently. Where the normal rules of planetary geology and atmospheric science break down, where terms like atmosphere and core might not even apply in the ways we understand them. The planet is being constantly bombarded by radiation that would sterilize any surface. Its magnetic field, if it has one, must be extraordinarily strong to deflect the pulsar's magnetic field. Its interior temperature might be elevated not by internal radioactive decay, but by tidal heating, the constant flexing and stretching from the pulsar's gravity, generating heat through friction. And yet it survives, orbits, persists. The pulsar has been spinning for millions of years, possibly billions. The planet has been orbiting for just as long. It hasn't been destroyed. It hasn't been torn apart. It hasn't spiraled inward or been flung outward. It exists in a state of equilibrium that seems impossible, but clearly isn't. Because it's there. We can measure it. We can time its orbit. We can calculate its mass. It is as real as Earth, as real as Jupiter, as real as any planet in our solar system. But it exists in a context that makes it fundamentally alien. Not just alien life, alien geology, alien physics, alien in ways that challenge our ability to even conceptualize what we're observing. The formation scenarios are equally puzzling. Did the planet form before the supernova, somehow surviving the explosion at a great distance before migrating inward? Did it form after, coalescing from the debris disk around the newly formed pulsar? Was it captured, pulled in from another system by gravitational interaction? Each scenario has problems. Surviving a supernova at close range seems impossible. Forming from supernova debris should produce smaller, rocky planets, not gas giants. Capture requires incredibly specific conditions and is statistically unlikely. Yet one of these scenarios must be true. Or there's a fourth option we haven't thought of yet. An option that doesn't fit into our current models of planetary formation. An option that would require rewriting parts of astrophysics. The researchers who study PSR J2322-2650b speak carefully. They use words like unusual and unexpected and challenging to explain. They propose models and run simulations. They compare the system to other pulsar planets, of which there are only a handful known. They search for patterns. They write papers suggesting formation mechanisms, each one provisional, each one hedged with caveats and uncertainties. Because the truth is, they don't know. Not really. They have observations, they have data, they have measurements, but the explanation, the satisfying, complete explanation that ties everything together, that makes sense of how and why this planet exists, that explanation doesn't exist yet. Maybe it will. Maybe in 5 years or 10 years, someone will have an insight that makes it all click into place. Or maybe PSR J22322265 FeroB will remain mysterious. A data point that doesn't fit. A planet that exists but shouldn't. A lemon-shaped reminder that the universe is under no obligation to make sense to us. The telescope data came back corrupted. That's what they thought initially. The transit observations of WASP 193b showed a planet crossing in front of its star, blocking a portion of the star's light. From this, astronomers can calculate the planet's size. The more light blocked, the larger the planet. WASP 193b blocked a lot of light. It was big, bigger than Jupiter. But when they calculated its mass using radial velocity measurements, tracking the wobble the planet induced in its star, the number was impossibly low. The planet was massive, yes, but not massive enough. Not for its size. The density they calculated was absurd. Lower than Saturn, lower than any planet in our solar system. Lower than water, lower than cork. Lower, in fact, than cotton candy. The team checked their instruments. They recalibrated. They looked for errors in the data processing pipeline. They found none. They made new observations. The results were the same. WASP 193b had a radius about 50% larger than Jupiter, but a mass only slightly greater. Its average density worked out to roughly 0.059 grams per cubic centimetre. For context, Jupiter's density is about 1.3 grams per cubic centimetre. Earth's is 5.5. Water is 1.0. Styrofoam is around 0.05. Cotton candy is approximately 0.05 to 0.1. WASP 193b was less dense than cotton candy, an entire planet, larger than the largest planet in our solar system, with a density so low it would float in water if you could find a bathtub large enough. This shouldn't be possible. Gas giants are made of hydrogen and helium, the lightest elements in the universe. But even hydrogen and helium have mass. Compress enough of it together, and the planet should collapse under its own gravity, becoming denser. Jupiter demonstrates this. Saturn demonstrates this. All known gas giants demonstrate this. There's a relationship between mass and radius for gas giants, a curve that describes how big a planet should be given its mass. WASP 193b doesn't fit on that curve. It's far above it, in a region that physics says should be empty. Its radius is too large. Its density is too low. Its very existence is an anomaly. The planet orbits its star very closely, completing an orbit every 6.25 days. This proximity means it's hot, very hot. The star bathes it in intense radiation, heating its atmosphere to over 1,200 degrees Celsius. Hot planets tend to have inflated atmospheres. The heat causes the atmosphere to expand, making the planet appear larger. This is well understood. Dozens of hot Jupiters show this effect. But WASP 193b is inflated beyond anything those models predict. It's not just a little bigger than it should be. It's spectacularly, absurdly, inexplicably bigger. Its atmosphere extends so far from its core that the planet is more atmosphere than anything else. A gossamer shell of hydrogen and helium spread so thin that it barely qualifies as matter, held together by a gravity field that seems far too weak to do the job. Scientists have proposed several mechanisms for atmospheric inflation in hot Jupiters. Tidal heating, where gravitational interactions with the star generate internal heat. ohmic heating, where electrical currents in the atmosphere dissipate energy. Delayed cooling, where the planet's interior stays hot longer than expected. Each mechanism can inflate a planet somewhat, but WSP-193b requires all of them working together at maximum efficiency, and even then, the models struggle to reproduce what's observed. It's as if the planet is being inflated by something we haven't accounted for, some energy source or mechanism that doesn't appear in our equations. Something that keeps pumping energy into the atmosphere, preventing it from collapsing to a more reasonable density. One possibility is that the planet's atmosphere is extremely efficient at absorbing stellar radiation, more efficient than any other hot Jupiter we've found. The radiation heats the upper atmosphere, which then radiates that heat downward, heating lower layers, creating a temperature inversion that resists gravitational collapse. But even this scenario requires fine-tuning. The atmosphere must be transparent to certain wavelengths and opaque to others. It must circulate in specific ways to distribute heat evenly. It must maintain these properties over millions or billions of years, despite the constant bombardment from the star. The conditions required are not impossible, but they're extremely specific, and the fact that WSP-193b happens to exist in exactly those conditions seems suspiciously convenient. Another mystery is the planet's stability. An atmosphere that extended and tenuous should be vulnerable to atmospheric escape. The star's ultraviolet radiation should ionize the outer layers of the atmosphere, allowing them to stream away into space. This process, called photoevaporation, is thought to be responsible for stripping atmospheres from many close-in planets. Over time, WSP-193b should be losing mass. Its atmosphere should be shrinking. Eventually, it should collapse to a more normal density. But observations suggest it's stable. It's not shrinking. It's not losing mass at a rate that would significantly change its structure over the system's lifetime. Somehow, it's maintaining its impossibly puffy configuration despite being blasted by stellar radiation. The implications are unsettling. If WSP-193b can exist, then our models of planetary atmospheres are missing something fundamental. Some planets might be able to maintain ultra-low densities through mechanisms we don't understand. This means there could be more planets like WSP-193b out there waiting to be found. Planets that challenge our definitions and categories. Planets that exist in states we thought were forbidden. And if we're wrong about this, what else are we wrong about? What other impossible configurations might exist? What other categories of planet have we failed to imagine? There's also the question of interior structure. A planet that puffy must have a relatively small core. Most of the planet's volume is atmosphere, but there must be something solid or liquid at the center, something providing the gravitational seed around which the atmosphere accreted. What is that core made of? How massive is it? Is it a rocky core like Jupiter's, or something more exotic? The planet's low overall density suggests the core must be small, but how small? And what's the transition like between the core and the atmosphere? Is there a sharp boundary, or does the atmosphere gradually compress as you descend, transitioning smoothly from gas to liquid to solid? These questions can't be answered with current technology. We can measure the planet's size and mass, but we can't see inside it. We can only infer. And our inferences are guided by models that WSP-193b has already demonstrated to be inadequate. The discovery was published in 2024, and the astronomical community is still grappling with its implications. Some researchers have proposed that WSP-193b might be uniquely young, still in the process of contracting and cooling, and that we're seeing it in a temporary inflated state that will eventually subside. But the system's estimated age doesn't support this. Others suggest that the planet's composition might be unusual, with a higher proportion of heavy elements that alter its thermal properties. But the spectroscopic observations don't show evidence of this. Every conventional explanation runs into problems. Every model requires tweaking, special pleading, fine-tuning to match the observations. And in science, when you have to adjust your theories too much to fit one data point, it often means you're missing something bigger, something fundamental. WASP 193b floats in space right now, impossibly puffy, impossibly stable, impossibly real. It orbits its star every 6.25 days, ballooning larger than Jupiter despite having a fraction of Jupiter's mass. Somewhere inside that vast, tenuous atmosphere is a core, a remnant of the solid material from which the planet formed. And surrounding that core is layer upon layer of hydrogen and helium, stretched so thin that the boundary between atmosphere and space is almost arbitrary. The planet is a ghost, a wisp, a soap bubble on a cosmic scale, and yet it endures. It exists, and it demands explanation. An explanation that so far we cannot provide. The star 55 Cancri is visible to the naked eye. It's about 41 light-years away, a relatively nearby neighbour in galactic terms. It's been known for centuries, catalogued, studied. In the early 2000s, astronomers discovered it had planets, 5 of them in fact, making it one of the first multi-planet systems found around a sun-like star. The planets were named 55, Cancri B, C, D, E and F. Planet E was the closest to the star, innermost, a world that completed one orbit every 18 hours, a year that lasts less than a day. The planet was small, only about twice Earth's diameter, but significantly more massive, about 8 times Earth's mass. A super-Earth, rocky, dense, and unimaginably hot. The temperature on 55 Cancri's surface exceeds 2,700 degrees Celsius. Hot enough to melt lead. Hot enough to vaporize water instantly. Hot enough that rocks themselves might be liquid. The planet is tidally locked, meaning one side always faces the star, eternally day, while the other side faces away, eternally night. The day side is a furnace. The night side, while cooler, is still hot by any reasonable standard, likely over 1,000 degrees Celsius, due to heat transported by the atmosphere, if there is an atmosphere. The planet orbits so close to its star that it's essentially grazing the outer layers of the star's atmosphere. It should have been consumed, or at least stripped of any volatile materials, reduced to a bare iron core. But 55 Cancri A is more interesting than that. Early observations suggested the planet's density was higher than expected for a rocky body. This implied a high proportion of heavy elements, carbon in particular. Carbon is abundant in the universe, the 4th most common element. It forms in stars and is scattered into space when those stars die. Planets that form in carbon-rich environments can have unusual compositions. Instead of silicate rocks like Earth, they might have carbide rocks. Instead of an iron core, they might have a core of crystallized carbon, diamond. The idea emerged that 55 Cancri A might be a carbon planet, a world where the dominant mineral isn't silicon dioxide, but carbon in various forms. A planet where the geology is based on carbon chemistry rather than silicon chemistry. A diamond planet. The concept captivated the public imagination. Headlines declared that a planet worth vast fortunes had been found, a world covered in diamonds and jewels. But the reality is more complex and in some ways stranger. Even if 55 Cancri A has a diamond-rich interior, that diamond is not accessible. The surface temperature is hot enough to melt most materials. The pressure at the core is millions of times atmospheric pressure. The planet is 41 light-years away, far beyond the reach of any conceivable mining operation. The diamonds, if they exist, are purely academic, but scientifically, the implications are profound. A carbon-rich planet would behave differently than Earth. Its tectonics, if it has any, would operate under different rules. Its volcanic activity would produce different materials. Its interior structure would be fundamentally alien. But here's where the story becomes uncertain. Follow-up observations using more advanced techniques began to complicate the picture. Spectroscopic analysis of the planet's atmosphere, conducted using the Hubble Space Telescope and later the James Webb Space Telescope, revealed evidence of volatiles, gases like carbon dioxide and possibly carbon monoxide. This suggested the planet wasn't a bare rock after all. It had an atmosphere, not a thick one, not like Earth's, but a tenuous envelope of gas. Where did that gas come from? On a planet as hot as 55 Cancri A, any primordial atmosphere should have been stripped away billions of years ago by stellar wind and radiation. The atmosphere must be secondary, replenished, generated continuously by some ongoing process. The most likely source is volcanic outgassing. If the planet has a molten interior, and it almost certainly does given the tidal heating from its proximity to the star, then volcanic activity would release gases from the interior to the surface. These gases would form an atmosphere. That atmosphere would then be slowly stripped away by stellar radiation, but as long as volcanic activity continues, it would be replenished. This creates a dynamic equilibrium, an atmosphere that exists not because it's stable, but because it's constantly being recreated. The planet is leaking gas into space even as it generates more gas from below. It's a planet in flux, a world where the surface and atmosphere are not fixed but constantly churning, constantly renewing. But this raises a new question. What kind of lava does a carbon-rich planet have? On Earth, lava is mostly silicate, melted rock composed of silicon and oxygen with various other elements mixed in. But on a carbon planet, lava might be something else entirely. Melted carbides, liquid carbon, graphite flows. The very concept strains our vocabulary because we don't have direct experience with these materials in molten form on a planetary scale. Laboratory experiments can simulate some of these conditions, but extrapolating from tiny samples in a lab to an entire planet's geology is fraught with uncertainty. The lava on 55 Cancri E might be black or shiny or something in between. It might flow differently than Earth lava, have different viscosity, different cooling rates. It might crystallize into forms we can only guess at. And then there's the diamond core hypothesis. Deep inside the planet, under the pressure of millions of atmospheres, carbon would be compressed into its densest form. Diamond. Not the small gem-quality diamonds found on Earth, but a massive structure, possibly thousands of kilometers across. A core of compressed carbon, surrounded by layers of less compressed carbon, surrounded by a mantle of carbide rock, surrounded by a thin crust and atmosphere. The transition zones between these layers would be regions of exotic chemistry and physics. Diamond doesn't behave like iron. It doesn't conduct heat the same way. It doesn't respond to pressure the same way. A planet with a diamond core would have different thermal properties, different seismic properties, different magnetic properties. It would be, in the most literal sense, a different kind of world. But we don't know for certain that the diamond core exists. The evidence is indirect. We know the planet's mass and size, which gives us its average density. We can estimate its composition based on the star's composition and models of planetary formation. We can infer what the interior might look like based on pressure and temperature calculations. But we can't see inside the planet. We can't drill into it or send a probe through its crust. All we have are models, and models are only as good as the assumptions they're built on. If those assumptions are wrong, if carbon planets don't work the way we think they do, then the diamond core might not exist. Or it might exist but be smaller than we think, or larger, or mixed with other materials, or in a form we haven't anticipated. The atmosphere adds another layer of mystery. Spectroscopic observations show evidence of hydrogen and helium alongside the carbon dioxide, suggesting the atmosphere is a complex mixture. How does this mixture behave? How does it circulate? The planet's tidal locking creates extreme temperature gradients. The day side is far hotter than the night side. This should drive powerful atmospheric circulation, winds carrying heat from the day side to the night side. But with what efficiency? How fast are the winds? Do they create weather patterns, storms, cyclones? Or is the atmosphere too thin for that, too tenuous to support anything we would recognize as weather? These questions remain unanswered. The observations give us hints, glimpses, but not a complete picture. There's also the question of the planet's history. Did it form where it is now, or did it migrate inward from a more distant orbit? If it migrated, it might have started as a more conventional super-Earth, perhaps even with water, before drifting closer to the star and being transformed into the hellish world it is today. Or it might have formed in place, coalescing from the inner disk of the protoplanetary system, always hot, always carbon-rich. The formation scenario affects our understanding of the planet's composition. A migrated planet would have different chemical fingerprints than an in situ planet. But determining which scenario is correct requires more data than we currently have. We need better spectroscopy, better atmospheric models, better understanding of planetary migration mechanisms. We need observations that can distinguish between these scenarios, and we're not quite there yet. So 55 Cancri A remains enigmatic, a super-Earth orbiting closer to its star than any planet in our solar system. A world of molten rock and possible diamonds. A planet with an atmosphere that shouldn't exist but does. A laboratory for extreme geology, a testing ground for planetary science's most exotic predictions. It's close enough that we can study it in some detail, far enough that we can't study it in complete detail. We see enough to know it's strange, not enough to know exactly how strange. And that gap, that space between what we observe and what we understand, is where the mystery lives, where the questions accumulate, where the planet becomes more than just a data point in a catalogue. It becomes a puzzle, a challenge, an invitation to reconsider what we think we know about how planets work, because if 55 Cancri A can exist, if a diamond world bathed in starlight and heat can orbit a nearby sun, then what else is possible? What other exotic compositions and configurations are waiting out there in the thousands of planetary systems we've discovered and the billions we haven't? The image was unremarkable at first glance, just another observation from the James Webb Space Telescope, another infrared survey of a star-forming region. The Orion Nebula, about 1,350 light-years away, has been studied for decades. It's a stellar nursery, a vast cloud of gas and dust where new stars are being born. Astronomers point telescopes at it regularly, cataloguing the young stars, studying their properties, understanding how stellar formation works. But in 2023, an image revealed something unexpected. Not stars, or not exactly stars. Objects too small to be stars, too isolated to be planets, floating freely in the nebula, untethered to any parent star. And some of them weren't alone. Some of them had companions, orbiting each other, binaries, Jupiter-mass objects in binary pairs, moving through space together, gravitationally bound, but belonging to no stellar system. The researchers called them jumbos, Jupiter-mass binary objects. And they shouldn't exist. Planets form in disks around stars. This is the standard model. A young star is surrounded by a rotating disk of gas and dust. Over time, particles in the disk collide and stick together, growing larger. Dust grains become pebbles. Pebbles become rocks. Rocks become planetesimals. Planetesimals collide and merge, forming planets. Gas giants like Jupiter form when a rocky core grows large enough to gravitationally capture huge amounts of hydrogen and helium from the disk. This process requires a star. The star provides the gravitational center around which the disk orbits. The star provides heat and radiation that affect the disk's chemistry and dynamics. Planets are, by definition, objects that form in orbit around stars. They are not independent. They are not free-floating. They are children of their stars. But jumbos are free-floating. No star, no orbit, just drifting through the nebula, carried by the slow currents of gas and dust. And they're not small. They have masses comparable to Jupiter, hundreds of times the mass of Earth. Objects that massive don't just appear, they must form somehow. But if they didn't form around a star, how did they form? Stars form when dense regions of a gas cloud collapse under their own gravity. If the collapsing region is massive enough, the core heats up until nuclear fusion ignites and a star is born. If the region is too small, fusion never starts, and the object becomes a brown dwarf, a failed star. Brown dwarfs are well known. They're too massive to be planets, too light to be stars, occupying a grey zone between the two. But brown dwarfs are typically at least 13 times Jupiter's mass, the minimum needed to fuse deuterium. Jumbios are less massive than that. They're in the planetary mass range. But they appear to have formed like stars, through direct gravitational collapse, not through accretion in a disk. They blur the line between planets and stars in a way that challenges our definitions. And then there's the binary problem. About 10% of the jumbos found in the Orion Nebula are in binary pairs. Two Jupiter-mass objects orbiting each other, separated by distances of hundreds of astronomical units. Binary stars are common. About half of all stars are in binary or multiple systems. But binary planets? That's not supposed to happen. If two objects form in a protoplanetary disk, they should either collide and merge, or one should eject the other, or they should remain in orbit around the star in different orbits. Having two planetary mass objects orbit each other while both orbit a star is possible, but rare. Having two planetary mass objects orbit each other with no star at all? That's new. That requires a formation mechanism that can produce two similar mass objects in close proximity without a central star to organize the system. One hypothesis is that jumbos form like stars from the collapse of a gas cloud, but in regions where the gas density is too low to produce a stellar mass object. The cloud fragments, collapsing into multiple smaller pieces, each of which becomes a Jupiter mass object. If two of these fragments are close enough, they remain gravitationally bound to each other, forming a binary. This is plausible. Computer simulations of star formation show that fragmentation can produce a range of masses, including objects in the planetary mass range. But the statistics are troubling. The number of jumbos found in the Orion Nebula is higher than models predict. If they form through fragmentation, there should be fewer of them. The fact that there are so many suggests either the models are wrong or there's another formation mechanism we haven't considered. Another hypothesis is that jumbos are planets that were ejected from their original stellar systems. Planetary systems are chaotic during their early evolution. Planets can interact gravitationally, their orbits shifting and changing. In some cases, these interactions can be violent enough to eject a planet entirely, flinging it out of the system into interstellar space. If two planets are ejected together in a close encounter that leaves them bound to each other, they could become a binary pair. This scenario is also plausible. Simulations show that planetary ejections happen. But the statistics, again, are problematic. The number of binary pairs is higher than ejection models predict. It's possible that both mechanisms are at work, some jumbios forming through fragmentation, others through ejection, but the relative contributions are unclear. There's also the possibility that we're seeing something genuinely new, a formation pathway that doesn't fit neatly into the categories of star formation or planet formation. A process that operates in the specific conditions of a stellar nursery, where gas and dust are abundant, where turbulence and magnetic fields create complex structures, where the boundaries between different formation mechanisms are blurred. Perhaps in these environments, objects can form that don't fit our existing definitions. Not quite planets, not quite brown dwarfs. Something in between. Something that exists because the universe's toolkit for making objects is richer than we realized. Something that forces us to expand our categories, to create new terms, to acknowledge that the neat boxes we use to classify celestial objects are human constructs, and nature doesn't necessarily respect them. The jumbos are still being studied. Follow-up observations are planned. Astronomers want to measure their masses more precisely, study their spectra to understand their composition, track their motion through the nebula to understand their history. Are they truly isolated, or are there faint stars nearby that we've missed? Are they young, recently formed, or old, ejected from systems long ago? Do they have disks of their own, circumplanetary disks that might form moons? Do they emit significant heat from gravitational contraction, or are they cool and dark? Each question requires data. Each question requires careful observation, and each answer will refine our understanding of what these objects are and how they came to be. But the philosophical implications are already clear. If jumbos exist, if Jupiter mass objects can form in isolation or be ejected in binary pairs, then the galaxy might be full of them. There could be billions of rogue planets drifting through interstellar space, invisible to most surveys because they don't orbit stars and emit very little light. Some of them might be alone, some might be in binary pairs, some might even have moons. The galaxy might be teeming with worlds that we've never accounted for, worlds that don't show up in our census of planetary systems because they're not part of any planetary system. They're orphans, nomads, wanderers in the dark. And if that's true, then our understanding of the galaxy's architecture, of how matter is distributed, of how common planets really are, all of that needs to be revised. The universe might be stranger, more populous, more filled with unexpected structures than we thought. And the jumbos are just the beginning, just the first hint of what else might be out there waiting to be found. The star Kepler-51 is about 2,600 light-years away in the constellation Cygnus. It was observed by NASA's Kepler Space Telescope, which stared at a patch of sky for years, monitoring the brightness of thousands of stars, looking for planets. The way the telescope found planets was simple but effective. When a planet crosses in front of its star, it blocks a tiny bit of light. The star dims slightly. Then when the planet moves away, the star brightens again. This is called a transit. By measuring the amount of dimming and the duration of the transit, astronomers can calculate the planet's size and orbital period. Kepler discovered thousands of planets this way. Most of them were normal, rocky planets, gas giants, ice giants, objects that fit into known categories. But Kepler-51 was different. The star had 3 transiting planets, labelled Kepler-51b, C and D. All 3 were roughly Neptune-sized, based on the amount of starlight they blocked. But when follow-up observations measured their masses using radial velocity techniques, the numbers were shocking. The planets were light, far too light for their size. Kepler-51b had a radius about 7 times Earth's, but a mass only about 2 times Earth's. Kepler-51c was similar. Kepler-51d was even more extreme, with a radius over 9 times Earth's, but a mass only a few times Earth's. The densities were comparable to cotton candy or styrofoam. These weren't just low-density planets, they were the lowest density planets ever found, and there were 3 of them, all in the same system, all defying explanation. The planets are often called superpuffs, a term that conveys their unusual nature. They're not just inflated, they're superinflated. Their atmospheres are so extended that they dominate the planet's structure. The solid or liquid core, if there is one, must be small, buried deep beneath layers of hydrogen and helium that stretch for tens of thousands of kilometers. The planets are more atmosphere than anything else. They're gossamer shells, barely there, held together by gravity fields that seem too weak for the job. And yet they exist, all 3 of them, orbiting their star in a compact configuration, all within 0.5 astronomical units, closer to their star than Earth is to the Sun. The question is why? Why are these planets so puffy? Why haven't their atmospheres collapsed under their own gravity? Why haven't they been stripped away by stellar radiation? The planets are young by astronomical standards, about 500 million years old. But that's still 500 million years. Plenty of time for atmospheric processes to take effect. Plenty of time for the planets to evolve toward more normal densities. Yet they remain superpuffs. Stable. Apparently unchanging. This stability is the central mystery. One hypothesis is that the planets are still contracting and cooling. Young planets are hot from the energy of formation, the countless collisions that built them. As they cool, they radiate that heat away, and their atmospheres contract. Perhaps Kepler-51's planets are still in this cooling phase, still contracting, and we're seeing them in a temporary inflated state. But the timescale is a problem. Theoretical models suggest that planets should cool and contract relatively quickly, on timescales of tens of millions of years. Kepler-51's planets are 500 million years old. They should have finished contracting by now, unless the cooling process is slower than we think. Unless there's a heat source we haven't accounted for, something keeping the atmospheres hot and inflated. Another hypothesis involves the planet's composition. Most gas giants are primarily hydrogen and helium, with small amounts of heavier elements. But if Kepler-51's planets have unusually low amounts of heavy elements, their atmospheres would be lighter, easier to inflate. The lack of heavy elements could come from the formation environment. If the planets formed in a region of the protoplanetary disk that was depleted in solids, they would accrete less rock and ice, resulting in lower mass cores and lighter overall compositions. This could allow their atmospheres to inflate more easily. But even this scenario has limits. There's only so much you can reduce the heavy element content before the planet can't form at all. And the superpuffs are right at that edge, teetering on the boundary of what seems physically plausible. A third hypothesis involves atmospheric escape, but in reverse. Instead of losing atmosphere, the planets might be gaining mass from some source. Perhaps they're accreting material from a residual gas disk around the star. This would add mass to the atmospheres, potentially balancing atmospheric loss and maintaining the inflated state. But Kepler-51 shows no evidence of a significant gas disk. The star is hundreds of millions of years old. Any primordial disk should have dissipated long ago. There's no obvious source for the gas that would need to be accreted, unless the disk is there but invisible to our current instruments, unless the accretion rate is so low that we can't detect it, but still high enough to matter over millions of years. These are not impossible scenarios, but they're speculative. They require conditions that are hard to verify. There's also the intriguing possibility that the planet's atmospheres are held up by internal heat sources. Tidal heating, generated by gravitational interactions with the star or with each other, could warm the planet's interiors, generating heat that flows upward into the atmospheres, preventing them from cooling and collapsing. But the planet's orbits are not particularly elliptical, which limits tidal heating. and they're spaced far enough apart that tidal interactions between them should be weak. The amount of heat generated might not be enough to maintain the observed inflation. Unless the planet's interiors are more efficient at converting tidal energy into heat than we think. Unless there are resonances or interactions that amplify the effect. Again, possible, but uncertain. Each explanation runs into problems. Each requires fine-tuning or special conditions. And the fact that there are 3 such planets in one system makes it even harder to explain. If superpuffs are the result of rare, unusual circumstances, why would 3 of them form around the same star? It seems unlikely. It suggests that whatever process creates superpuffs might not be as rare as we think. That there might be something about the Kepler-51 system's formation or evolution that naturally produces these planets. But what? What property of the protoplanetary disk, or the star, or the planet's orbital configuration leads to this outcome? We don't know. The data doesn't give us enough information to choose between competing hypotheses. What we can say is that the planets are there, 3 of them, superpuffs, defying our expectations, challenging our models. Spectroscopic observations have been attempted, trying to study the planet's atmospheres during transits, looking at the starlight that filters through the upper atmosphere to identify chemical signatures. But the results have been ambiguous. The atmospheres are so extended and hazy that they obscure the spectral features. The data shows evidence of clouds or hazes at high altitudes, thick enough to block most of the light, preventing us from seeing deeper into the atmosphere where more interesting chemistry might be happening. The planets are hiding their secrets behind veils of mist. Future observations with more advanced telescopes might pierce those veils. The James Webb Space Telescope has the sensitivity to probe these atmospheres in more detail, to look at longer wavelengths where the clouds might be more transparent. Observations are planned, data will be collected, analysis will be done. Perhaps in a few years we'll have a clearer picture of what these planets are made of, what their atmospheres are doing, why they're so impossibly inflated. Or perhaps we'll just find new mysteries, deeper questions, more layers of strangeness. Because that's often how science works. You answer one question and 2 more appear. You peel back one layer and there's another beneath it. The universe is not a simple puzzle with a single solution. It's a fractal, complexity at every scale, strangeness all the way down. And now we need to ask the question that's been lurking beneath all of these discoveries. What does it mean that these planets exist? Not just as individual curiosities, but as a collective set of data points that don't fit our models. PSR J232265b orbits a pulsar and is shaped like a lemon. WASP 193b has the density of cotton candy. 55 Cancri might have a diamond core. Jumbos float freely in space, some in binary pairs. The Kepler-51 planets are superpuffs, inflated beyond reason. Each of these discoveries was published, peer-reviewed, confirmed. They are not errors, they are not artifacts. They are real objects existing in our universe, subject to the same laws of physics as everything else. And yet they defy our understanding. They sit outside the predictions of our models. They occupy regions of parameter space that we thought were empty or impossible. What does that tell us? One possibility is that we're simply underestimating the diversity of planetary systems. The planets in our solar system are a tiny sample. 8 planets around one star. We thought for a long time that our solar system was typical, that other systems would look similar. Rocky planets close to the star, gas giants farther out, ice giants at the edges, a neat, organized structure. But the first exoplanets discovered were hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun. That alone shattered our assumptions. Then we found super-Earths, planets larger than Earth but smaller than Neptune, a category that doesn't exist in our solar system but appears to be common in others. Then we found systems with planets in orbits that would be unstable in our solar system. Then we found planets around binary stars, around pulsars, around white dwarfs. Every new discovery has expanded the range of what's possible. Perhaps the strangest planets are just the latest expansion. Perhaps they're showing us that the universe's creativity exceeds our imagination, that planets can exist in configurations we never thought to consider. Another possibility is that our models are incomplete. Not wrong, but incomplete. Missing pieces, missing processes, missing interactions. Planetary formation is incredibly complex. It involves gravity, thermodynamics, fluid dynamics, chemistry, magnetic fields, radiation, collisions, migrations, resonances. Each of these factors can affect the outcome, and they don't operate independently. They interact, sometimes in ways that amplify small differences, creating outcomes that are sensitive to initial conditions. It's possible that the strangest planets form in edge cases, in situations where multiple factors combine in unusual ways. The models we use are simplifications. They have to be. You can't simulate every interaction at every scale. You make approximations, you focus on the dominant effects. But sometimes the subdominant effects matter. Sometimes the details that seem negligible turn out to be crucial. And if those details aren't in your model, you'll miss the predictions. You'll be surprised when reality produces something your equations didn't anticipate. A third possibility is more unsettling. What if these planets are telling us that our understanding of physics itself is incomplete? Not at the fundamental level, not the laws of thermodynamics or gravity or quantum mechanics. Those are well tested. But in how those laws apply to complex systems, to objects at planetary scales, to conditions we can't replicate in laboratories. There might be regimes where our equations have solutions we haven't explored, behaviors that emerge from the interactions of known physics but that we haven't predicted because we haven't looked for them. The strange planets might be occupying those regimes, showing us corners of the solution space that we didn't know existed, demonstrating that even with the laws of physics as we understand them, the outcomes can be far stranger than we expected. Or maybe it's simpler. Maybe we're just bad at predicting rare events. The universe is vast. There are billions of stars, trillions of planets. Most of them are probably normal, fitting into our models, orbiting their stars in predictable ways. But when you have trillions of chances for something weird to happen, the weird things will happen. Rare configurations will occur. Unlikely sequences of events will play out. And because we're looking at thousands of planetary systems now, we're starting to see those rare cases. The lemon planet, the cotton candy planet, the diamond world, the rogue binaries, the superpuffs. They're outliers, statistical flukes, the tales of the distribution, not impossible, just improbable. And improbable things become probable when you have enough trials. The universe is rolling the dice billions of times, and we're finally seeing the strange outcomes that occur once in a million or once in a billion tries. But even if that's true, it doesn't fully answer the question. Because the existence of these planets forces us to expand our conception of what planets can be. They're not just data points, they're examples, proof that certain configurations, certain processes, certain outcomes are possible. And if they're possible, then there might be others we haven't found yet. More extreme examples, weirder configurations, planets that make the ones we've discovered look tame by comparison. The universe has shown us its hand, and the cards it's playing are stranger than we expected. What other cards does it have? What else is possible that we haven't imagined? There's also an epistemological question. How do we know when we understand something? In physics, understanding usually means prediction. You have a theory. You make a prediction. You test the prediction. If the test confirms the prediction, your theory is supported. If it doesn't, you revise the theory. But planetary science is different. We can't run controlled experiments. We can't create planets in laboratories and watch them evolve. We can only observe. We see the outcomes, but not the processes. We see the final states, but not the intermediate steps. Our theories are reconstructions, inferences from incomplete data. And when the data shows us something we didn't predict, it's not always clear what went wrong. Was it a bad assumption? A missing factor? A computational error? Or is reality just more complex than our models? Sorting through these possibilities is slow, difficult work. It requires more data, better observations, refined models. And even then, there's no guarantee we'll reach a definitive answer. Some mysteries might remain unsolved for decades. What's certain is that these discoveries have energized the field. Planetary science is no longer just about understanding our solar system. It's about understanding planetary systems in general, in all their diversity. It's about cataloging the full range of what planets can be, how they form, how they evolve, how they die. It's about building models that are robust enough to explain not just the common cases, but the rare ones too. It's about recognizing that the universe is not obligated to make things easy for us, that nature operates on its own terms, following rules that are consistent but not always intuitive, and that our job as scientists is to figure out those rules, to decode the patterns, to understand the mechanisms, to build a picture of reality that matches what we observe, not just what we expected to observe. The strangest planets are teachers. They're showing us where our knowledge ends and our ignorance begins. They're pointing to the gaps in our understanding, the areas where our models are thin or incomplete. They're challenging us to think more creatively, to question our assumptions, to consider possibilities we dismissed as implausible. And in doing so, they're pushing the boundaries of what we know about the universe. They're expanding our conception of planetary science, moving it from a field focused on explaining the familiar to one capable of grappling with the truly bizarre. This is how progress happens, not smoothly, not predictably, but through encounters with the unexpected, through the collision of theory and observation, through the humbling realization that reality is richer, stranger, and more wonderful than we imagined. Let's return to the Lemon Planet, PSR J232222654b, stretched by the gravity of its pulsar host, distorted into an ellipsoidal shape, a Jupiter-mass world in one of the most hostile environments imaginable. The pulsar emits radiation that would sterilize any surface. The magnetic fields are strong enough to affect the planet's interior structure. The tidal forces are powerful enough to generate heat through constant flexing, and yet the planet endures. It has been there for millions of years, possibly billions. It has not been torn apart. It has not been ejected. It has not spiraled into the pulsar. It orbits, stable, persistent, a world that exists in defiance of every intuition we have about what environments are compatible with planetary survival. The formation of this planet is a puzzle that researchers are still working to solve. One scenario is that it formed before the supernova, in orbit around the progenitor star. When the star exploded, the planet was far enough away to survive, but the explosion would have stripped away its outer layers, leaving behind a denser core. The core would then have migrated inward, pulled by gravitational interactions with the debris disk around the newly formed pulsar. This scenario explains the planet's existence but requires very specific conditions. The planet must have been at just the right distance to survive the supernova, but close enough to be captured by the pulsar's gravity. The odds of this happening are low, but not zero. And we've found other planets around pulsars, though none as massive as PSR J232222654b, suggesting that this formation pathway, while rare, is possible. Another scenario is that the planet formed after the supernova from the debris disk itself. Supernovae produce large amounts of heavy elements which are scattered into space and can form disks around the remnant star. These disks could, in theory, form planets, but the timescale is problematic. Disk material around pulsars dissipates relatively quickly, on timescales of millions of years. Forming a Jupiter-mass planet in that time is challenging. Most models suggest that planets forming in pulsar disks would be small, rocky worlds, not gas giants. PSR J2322265LB doesn't fit this profile. It's too massive. Its composition, inferred from models, suggests it contains significant amounts of hydrogen and helium, which wouldn't be abundant in a supernova debris disk. So this scenario, while possible, seems less likely. A third scenario is capture. The pulsar might have encountered a free-floating planet, a rogue world drifting through interstellar space, and captured it through gravitational interaction. This would explain the planet's mass and composition. Rogue planets exist. We found evidence of them. Jumbos are examples. If rogue gas giants are common, then capture becomes a viable formation mechanism. But the dynamics are tricky. Capturing a planet requires shedding energy, usually through a three-body interaction or through drag from a gas disk. Without such mechanisms, the planet would just swing past the pulsar and continue on its way. So capture requires not just proximity, but also specific conditions that allow the planet to lose enough energy to become bound. These conditions are rare, but not impossible. And given the number of pulsars in the galaxy and the possible abundance of rogue planets, capture events probably happen. We just don't know how often. Each scenario has problems. Each requires assumptions or special conditions, and none of them can be definitively ruled out with current data. What we need are more observations, better measurements of the planet's mass, its orbit, its composition. Spectroscopic analysis, if possible, to identify chemical signatures in the planet's atmosphere. Comparison with other pulsar planets to see if there are patterns or commonalities. And more theoretical work, refining the models, exploring the parameter space, identifying observational tests that could distinguish between competing formation scenarios. This is the slow, careful process of science. Building understanding piece by piece, testing ideas against data, revising when necessary, persisting despite uncertainty. But even without definitive answers, PSR J232222650b tells us something important. It tells us that planets can exist in environments we thought were incompatible with planetary survival, that the boundaries of the habitable zone, the region around a star where conditions are suitable for life, are perhaps too narrowly defined. Not habitable in the sense of life, not on a planet orbiting a pulsar, but habitable in the sense of planetary existence. The universe is more permissive than we thought, more willing to allow planets to form and persist in extreme conditions. And if that's true for pulsars, what about other extreme environments? What about planets around black holes, if such things can exist? What about planets in the dense cores of globular clusters, where stellar interactions are frequent and violent? What about planets in the outskirts of galaxies, far from the gravitational influence of the galactic center? The existence of PSR J232222650b expands the realm of possibility. It suggests that planets might be even more common, more resilient, more diverse than we've dared to imagine. WASP 193b, the cotton candy planet, poses a different kind of challenge. It's not about survival, it's about structure. How can a planet so large have so little mass? How can it maintain such an extended atmosphere without collapsing? The planet orbits its star every 625 days, bathed in radiation. This radiation heats the atmosphere, causing it to expand. This much is understood, but the degree of expansion is far beyond what models predict. The planet's radius is about 50% larger than Jupiter's, but its mass is only slightly more. The density is about 0.059 grams per cubic centimetre. For comparison, the density of air at sea level on Earth is about 0.0012 grams per cubic centimetre. WSP-193b's atmosphere is denser than air, but not by much. It's a tenuous, fragile structure, held together by gravity that seems barely strong enough for the job. The energy budget is the key issue. The planet absorbs energy from its star. That energy heats the atmosphere. The hot atmosphere expands. But eventually, the expansion should stop. The planet should reach an equilibrium where the energy it absorbs equals the energy it radiates away. At that equilibrium, the planet should have a specific size, determined by its mass, composition, and the amount of stellar radiation it receives. WSP-193b is not at that equilibrium, or if it is, the equilibrium is far from where models say it should be. Something is adding energy to the system, keeping the atmosphere hot and inflated. But what? One possibility is that the planet's atmosphere is very efficient at absorbing stellar radiation. Most hot Jupiters have atmospheres that are partially transparent to visible light, allowing some energy to pass through to deeper layers. But if WSP-193b's atmosphere is opaque to most wavelengths, it would absorb more energy, heating the upper layers, which would then radiate that energy downward, heating the lower layers. This creates a temperature inversion, where the temperature increases with altitude instead of decreasing. Temperature inversions can resist gravitational collapse, maintaining inflated structures. But creating such an inversion requires specific atmospheric chemistry. You need molecules or particles that are good at absorbing radiation at the wavelengths the star emits. Candidates include titanium oxide and vanadium oxide, which absorb visible light, and various hazes or clouds. But spectroscopic observations of WSP-193b have not confirmed the presence of these molecules. The atmosphere is hazy, yes, but the exact composition of the haze is unknown. Without knowing what's in the atmosphere, it's hard to model how it absorbs and radiates energy. Another possibility is tidal heating, though this seems unlikely given the planet's orbital parameters. Tidal heating occurs when a planet's orbit is elliptical, causing the distance between the planet and star to vary. This variation creates tidal bulges that flex the planet's interior, generating heat through friction. But WSP-193b's orbit is nearly circular. The tidal heating should be minimal. Unless there's a companion planet or other gravitational influence that maintains some eccentricity, keeping the tidal forces active. But no such companion has been detected. The system appears to consist of just the star and WSP-193b, so tidal heating probably isn't the answer. A third possibility is that the planet is intrinsically hot, that it still retains heat from its formation, and that this residual heat is preventing the atmosphere from cooling and collapsing. Young planets are hot. They form through violent collisions, and the energy from those collisions heats the planet's interior. Over time, the planet cools, radiating that heat away. But if the cooling process is slow, if the planet's interior is insulated by a thick atmosphere, or if the heat transport mechanisms are inefficient, the planet could remain hot for hundreds of millions of years. WSP-193b's host star is estimated to be a few billion years old, which means the planet is at least that old. But few billion years is still relatively young in cosmic terms. Perhaps the planet hasn't finished cooling. Perhaps it's still in a transitional phase, still contracting, and we're observing it before it reaches its final, more compact state. This explanation has appeal because it doesn't require any exotic mechanisms. It's just a matter of timescale. but the models suggest that gas giants should cool on timescales of tens of millions of years, not billions. So if WASP 193b is still hot from formation, something is slowing down the cooling process. And we don't know what that something is. Or perhaps the answer is simpler. Perhaps the planet's core is very small. If the core contains very little rock and ice, if it's mostly hydrogen and helium, the planet's average density would be lower. A small core means less mass concentrated in the center, which means weaker gravity, which means the atmosphere can extend farther before the gravitational pull becomes strong enough to compress it. This scenario is consistent with the observations, but it raises its own questions. How does a planet form with such a small core? In the standard model of gas giant formation, you need a solid core of at least 10 Earth masses to gravitationally capture gas from the protoplanetary disk. If WASP 193b's core is smaller than that, how did it become a gas giant? Maybe it formed through a different process, through direct collapse of a gas cloud rather than core accretion. But direct collapse usually produces brown dwarfs or stars, not planets. And WASP 193b is definitely a planet. It's not massive enough to be a brown dwarf, so the formation pathway is unclear. What we're left with is a planet that exists but shouldn't, or at least shouldn't exist in the form we observe. A world that challenges our models at every turn, that forces us to reconsider assumptions we thought were solid. That suggests there are regimes of planetary structure we haven't fully explored. WASP 193b is not alone in its strangeness. There are other low-density planets, other hot Jupiters with inflated atmospheres. But WASP 193b is the most extreme case. It's the limit, the edge of what seems possible. And finding it tells us that the edge is farther out than we thought, that the range of planetary properties is broader, that the universe is capable of producing structures that strain our ability to explain them. And that should excite us, because it means there's still so much to learn, so much we don't understand, so many mysteries waiting to be unraveled. The diamond planet, 55 Cancri A, is perhaps the most evocative of all these worlds. The idea of a planet made of diamond captures the imagination in a way that low-density atmospheres and lemon-shaped worlds don't. It's tangible, comprehensible. You can picture it, even if the reality is far stranger and less accessible than the image suggests. But 55. Cancri A is not just a thought experiment. It's a real place, 41 light-years away, orbiting a sun-like star. A place where the surface temperature is hot enough to melt most metals, where the pressure deep inside is crushing, where carbon instead of silicon might be the dominant element in the planet's geology. A world that operates under rules we're only beginning to understand. The evidence for the diamond core comes from models of the planet's interior structure. Based on its mass and radius, we can estimate its average density. Based on the star's composition, which is relatively carbon-rich, we can infer that the planet formed in a carbon-rich environment. Carbon planets are predicted by planetary formation theory. If the protoplanetary disk has a higher ratio of carbon to oxygen than solar composition, the minerals that form will be carbon-based rather than silicon-based. Instead of silicates like quartz and olivine, you get carbides like silicon carbide and titanium carbide. Instead of a mantle of silicate rock, you have a mantle of carbide rock, and instead of an iron core, you might have a core of crystallized carbon, diamond. But the models are sensitive to assumptions. If the carbon to oxygen ratio is just slightly lower, the planet might not be a carbon planet at all. It might be a more conventional super-Earth, with a silicate mantle and iron core, just hotter and denser than Earth. The observations don't give us enough precision to distinguish between these scenarios. We know the planet's mass and radius. We have some spectroscopic data on its atmosphere, but we can't see inside the planet. We can't drill into it or send seismic waves through it. All we have are models, and models are only as good as their inputs. If the star's composition is slightly different than we think, if the planet's formation history involved mixing of materials from different parts of the disk, if the interior temperature or pressure is different than calculated, the predictions change. The diamond core might shrink or disappear entirely, replaced by something more conventional. But let's assume the models are correct. Let's assume 55 Cancri E does have a diamond core. What would that mean? Diamond is a form of carbon arranged in a crystal lattice. It's incredibly hard, incredibly strong, and incredibly dense compared to other forms of carbon like graphite. It's also transparent to visible light, but opaque to infrared, which affects how heat is transported through it. A planetary core made of diamond would conduct heat differently than an iron core. It would respond differently to pressure. It would have different seismic properties, different magnetic properties. If we could somehow study the planet's interior, if we could map its structure with the same detail we can map Earth's interior, we would find a geology that's alien. Not alien in the science fiction sense of being incomprehensible, but alien in the sense of being fundamentally different, based on different chemistry, operating under different rules. The planet's surface is another mystery. At temperatures of 2,700 degrees Celsius, rocks melt. If the surface is carbide-based, it would be molten carbide. Liquid silicon carbide. Flowing, churning, erupting in volcanic activity driven by heat from the planet's interior and from tidal forces. The surface might be dark, the color of graphite or coal, or it might be shiny, reflecting the star's light like polished metal. We don't know. We can't see the surface. The observations show evidence of an atmosphere, a tenuous layer of gas, but that atmosphere doesn't tell us what's beneath it. It obscures our view, adding another layer of uncertainty. And then there's the question of the atmosphere itself. The spectroscopic observations detected carbon dioxide and possibly carbon monoxide. These are volcanic gases. They suggest that the planet has active geology, that its interior is molten or partially molten, and that gases are being released from the interior to the surface. This is consistent with the high surface temperature and the tidal heating from the star. But the presence of hydrogen and helium in the atmosphere is puzzling. These light gases should have escaped long ago, stripped away by stellar wind and radiation. Their presence suggests they're being replenished. But how? Are they being outgassed from the interior, locked in minerals and released during volcanic eruptions? Or are they being captured from the stellar wind, flowing past the planet and being gravitationally trapped? Either scenario is possible, but the details are unclear. The observations give us hints but not a complete picture. The planet's history adds another layer of complexity. Did it form where it is now, or did it migrate inward from a more distant orbit? If it migrated, it might have started as a more conventional super-Earth, cooler, possibly even with water on its surface. As it drifted closer to the star, the temperature would have risen, the water would have evaporated, the atmosphere would have been stripped away, and the planet would have been transformed into the hellish world we see today. This scenario is plausible. Many hot Jupiters are thought to have migrated inward, and there's no reason super-Earths couldn't do the same. But proving migration requires evidence. Observations that can distinguish between an in-situ formation and a migration scenario. And we don't have those observations yet. The planet's current state doesn't tell us its past. It only tells us the present, what it is now, not how it got there. So 55 Cancri E remains enigmatic, a super-Earth, possibly with a diamond core, orbiting incredibly close to its star, with a secondary atmosphere and a surface of molten rock. a world that might represent a class of carbon planets or might be a unique configuration, a one-off result of specific formation conditions. We won't know until we find more planets like it. Until we can compare them, look for patterns, test theories against multiple data points. And that requires time, requires more observations, requires better instruments, requires patience and persistence. The diamond planet is not giving up its secrets easily, but it's there, orbiting its star, waiting for us to figure it out. And every observation, every data point, every refined model brings us a little closer to understanding what it is and how it came to be. The jumbos are perhaps the most philosophically challenging of all these discoveries, because they force us to confront the definitions we use. What is a planet? What is a star? Where do we draw the line? The International Astronomical Union defines a planet as an object that orbits a star, is massive enough to be rounded by its own gravity, and has cleared its orbital neighbourhood. By this definition, jumbos are not planets. They don't orbit stars. They're free-floating. So are they brown dwarfs? Brown dwarfs are objects too massive to be planets, but too light to sustain hydrogen fusion. They're failed stars. The boundary is usually set at about 13 Jupiter masses, the minimum needed to fuse deuterium. Jumbos are less massive than that, so they're not brown dwarfs either. They're something else, something in between, something we don't have a good name for yet. The discovery in the Orion Nebula was serendipitous. Astronomers were studying the nebula, looking at young stars, when they noticed objects that didn't fit, too faint to be stars, too massive to be planets, and unbound, not orbiting any star. Further analysis revealed dozens of them, some isolated, some in pairs, orbiting each other. The binary pairs were the real surprise. Binary stars are common, but binary planets? That requires a formation mechanism that can produce two similar mass objects in close proximity without a star. And we don't have a clear model for how that happens. One possibility is that jumbos form like stars, through the collapse of a gas cloud, but in regions where the gas density is too low to produce stellar mass objects. The cloud fragments, collapsing into multiple smaller pieces, each of which becomes a Jupiter mass object. If two fragments are close enough, they remain gravitationally bound, forming a binary. This is the direct collapse scenario. It's plausible. Computer simulations show that gas clouds can fragment in complex ways, producing a spectrum of masses. But the simulations also show that fragmenting clouds usually produce at least some stellar mass objects. The fact that we're finding so many substellar objects in the Orion Nebula suggests that either the fragmentation process is more efficient at producing low-mass objects than the models predict, or the nebula has unusual properties that favour low-mass formation. Another possibility is ejection. Planetary systems are dynamically unstable during their early evolution. Planets interact gravitationally, their orbits shifting. Sometimes these interactions are violent enough to eject a planet entirely. If two planets are ejected together, in a close encounter that leaves them bound to each other, they could form a binary pair. This scenario has been studied in simulations. It happens. But the statistics are problematic. The number of binary jumbos found in the Orion Nebula is higher than ejection models predict. It's possible that the models underestimate the ejection rate, or that the nebula has a high density of young planetary systems, increasing the likelihood of ejections. But it's also possible that ejection isn't the primary formation mechanism. A third possibility is that we're seeing a mix. Some jumbos formed through direct collapse. Some were ejected from planetary systems. Some might have formed through other mechanisms we haven't thought of yet. The Orion Nebula is a complex environment with dense gas clouds, intense radiation from nearby massive stars, magnetic fields, turbulence. There are many processes at work, and they interact in ways that are hard to predict. It's possible that jumbos are the result of multiple pathways, different objects forming in different ways but ending up with similar properties. Disentangling these pathways requires more data, more observations, more sophisticated models, and more comparison with other star-forming regions to see if jumbos are a common phenomenon or unique to the Orion Nebula. But regardless of how they formed, the jumbos are telling us something important. They're telling us that the boundary between planets and stars is blurry, that there's a continuum of objects from the smallest planets to the largest brown dwarfs, and that nature doesn't respect the categories we've imposed. The definitions we use are human constructs, created for convenience, for communication. They're not fundamental truths. Nature doesn't care about our definitions. It produces objects based on the laws of physics, and those laws don't have sharp boundaries. They produce a spectrum. And we're finding that spectrum is richer, more populated, more complex than we thought. The binary jumbos are particularly intriguing. Two objects, each with the mass of Jupiter, orbiting each other, separated by hundreds of astronomical units. No star, no external influence. Just two worlds, locked in a gravitational dance, drifting through space together. It's a system that shouldn't exist according to our previous understanding. Binary planets in orbit around a star are possible, though rare. But binary planets with no star? That requires a formation scenario that can produce two massive objects in proximity without a central gravitational anchor. And we're still working out what that scenario might be. The observations are clear. The jumbos exist. But the explanation is still being developed. It's in progress, uncertain, provisional. And that's okay. That's how science works. You find something unexpected, you try to understand it, you propose explanations, you test those explanations, you refine them, and slowly, over time, understanding emerges. Not all at once, not with certainty, but piece by piece, observation by observation, idea by idea. The Kepler-51 system is the culmination of all these mysteries. 3 planets, all superpuffs, all with densities lower than cotton candy, all in the same system, all defying explanation. If superpuffs were rare, finding 3 of them around one star would be extraordinary. It would suggest that something about the Kepler-51 system's formation or evolution creates conditions favourable for superpuff formation. But what? What makes this system special? What allows these planets to maintain their impossibly inflated atmospheres? One clue is the planets' masses. They're low. Kepler-51b is about 2 Earth masses. Kepler-51c is about 4 Earth masses. Kepler-51d is about 7 Earth masses. These are not massive planets. They're in the super-Earth range by mass, but they have radii comparable to Neptune or even larger. Their low masses mean their gravity is weak. Weak gravity means the atmosphere can extend farther before being pulled back down. But even accounting for this, the planets are more inflated than they should be. The models predict they should be smaller, denser, more compact. Something is keeping them inflated. Something is providing energy or preventing collapse. The planets of the Kepler-51 system orbit unusually close to their star, receiving enough radiation to heat and expand their atmospheres, but not nearly enough to explain why they are even more inflated than hot Jupiters, which are far more massive and endure much stronger stellar heating. This contradiction has led scientists to suspect that something unusual is happening inside these worlds. One possibility is that their atmospheres are extraordinarily light, composed almost entirely of hydrogen and helium, making them easy to puff up with relatively modest heat. Such atmospheres could form if the planets developed in a dust-poor region of the protoplanetary disk, though it's still unclear what process would have removed that dust in the first place. Another idea is ongoing atmospheric loss, driven by ultraviolet radiation from the star. Over time, this process can strip gas from a planet, but if that were happening at a significant rate, the planet should be shrinking and becoming denser, which we don't observe. Instead, the planets appear stable. This has shifted attention to a simpler explanation: youth. The system is only about 500 million years old, and the planets may still be cooling and slowly contracting from their formation. If so, we may be catching them in a temporary inflated phase. Complicating everything further are thick clouds or hazes high in their atmospheres, blocking deeper observations and influencing how heat is trapped. These hazes are not just an obstacle, they may be a key clue. Together, these puzzles make Kepler-51's superpuff planets an important testing ground, pushing planetary science to rethink how atmospheres form, evolve, and survive under stellar radiation.